Folks, excuse me. It's a little bit of sparkling water to get started here. So we're going to do this example of Gauss's theorem here, where you have a vector field and you have a particular area in the R3 plane, R3 space unit circle in the XY plane. So it's a two-dimensional uh, object or surface in that R3, and we're going to apply Gauss's theorem to this. And actually, I'm sorry, this is Stokes theorem section. I'm ahead of myself a little bit. We'll get to Gauss's theorem next time. So yeah, we're looking to apply Stokes theorem here. And so the very first thing is that we're going to calculate the line integral. Excuse me. The line integral over the boundary of C, this unit circle. So we know, for example, before we jump into that, well, we can go ahead and jump in. We're familiar enough that we kind of have done many of these. And the way this works is you need an alpha parametrization that parametrizes that C. And we've been doing this line integral equation since the beginning of time, really. We know that this is going to be 0 to 2 pi because this is one of the most fundamental parametrizations in the class. So the parametrization cosine sine, now because it's an R3, we're going to go ahead and throw a little 0 in there for the y coordinate. Excuse me. So let's go ahead and continue here with this integral. So 0 to 2 pi. Now, we need to plug this alpha into f. So this is the x, the y, the z. So the sine is going to have to go here. The cosine is going to go there, and the z is not going to go anywhere. So plugging alpha into f is going to look a little bit like this. The x is cosine. And that's going to be dot producted with the derivative of alpha. This is alpha here. So dot product with negative sine t, cosine t 0. Okay, continuing down here. The dot product is quite easy. We have positive 2 sine squared t plus so positive 2 sine t plus cosine squared t plus 0 dt. Okay, so this, we can't exactly apply Gauss's theorem, can we? But what we can do is we can't apply, sorry, I meant to say Pythagorean theorem. What we can do is we can break this 2 sine theta into 1 sine squared theta plus 1 sine squared theta plus cosine squared theta. And then we can say, hey, this is the Pythagorean identity of trig. So that's 1. So we can go ahead and come down here. Sine squared t plus 1. Okay, now we can apply our power reduction formula. So sine squared is always going to equal 1 minus cosine of 2 theta, or in this case, t. And that's just when you want to, whenever you want to, see, you can't naturally integrate a sine squared, so you need to reduce the power of it. And when you reduce the power, you're going to go ahead and have a couple extra problematic pieces, a 1/2, a distribution, a 2t instead of a t, but hey, at least it's not squared anymore. Okay, so continuing here, we have, let's see, so we just distribute this all out here. We have a 1/2, we have a 1/2 cosine 2t, and we have a 1. The 1 and the 1/2, let's go ahead and call that 3/2. Okay, integrating with respect to t, we have 3/2 t minus 1/4 sine 2t, evaluated from 2 pi to 0. Just remember that when you integrate cosine, it becomes sine, but more importantly here, the 2 that is in there will go to the bottom. That's how we get the 1/4. All right, let's go ahead and plug in this 2 pi now. So 3/2 times 2 pi minus, now if you plug in the 2 pi into sine, it's going to multiply with a 2. It's going to be 4 pi, regardless, sine of 0, 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, 12 pi. These are all 0, so we'll go ahead and mark that down as a 0. And usually students will plug in the 0 and say, hey, that's 0 as well. But be careful with these trig functions, right? Sometimes you plug in the 0 and it's not 0. In this case, sine of 0 is 0. So we're fine. So let's see, we have 3 pi is the answer. 3 pi is the answer of how much work this vector field does around that boundary, the boundary of this shape right here. Now, what does Stokes' theorem say? Stokes' theorem says that that should be equal to the, so that 3 pi that we got from the line, we got that from the line integral. The single line integral, f of alpha dot alpha prime. Stokes' theorem says that this is going to be equal to, and so we will verify this. This is kind of option number 2 when you're doing these problems is, hey, maybe you don't want to do the line integral. So we will do the double integral of the curl of the vector field dot the normal vector to the surface. The normal vector to this particular surface right there is, because that's lying in the xy plane, it's just 0, 0, 1. Now, what about the curl? The curl of this vector field up there, this vector field, you remember that the curl is a very long equation. It's the partial of fz minus the partial of fy with respect to a crisscross variable. So with respect to z here and y here. Likewise, we go f1, or sorry, fx, let's say, with respect to crisscross z and x. And then partial of the second coordinate variable minus the first, again, with respect to the crisscrossed parts. Now, if we look at our vector field, which is right there, we can see that FC is 0. So these two are 0. That's going to help. We can see that the x coordinate is negative 2y. Go ahead and put that right there. And we see that the y coordinate is x. So the curl here, we have 0, 0, 0, 0, 0, 0. Something went wrong there because we know this thing has to equal 3 pi. We cannot have a curl of 0. So let me check really quickly here. X minus z, y minus x, crisscrossed all the way. All of them are crisscrossed. Huh. Let's see. I put 0 here, 0 here. The x coordinate is negative 2y. That's right here, negative 2y. And oh my gosh, you see, guys, that's why you have to be a little careful. But you also see that doing the line integral helped me catch this error. This one is negative 2y, and the y coordinate is x, and that goes here. Okay, there's a little bit of a boo-boo. So let's see. So what do we have? This one is still 0, but it's this one here that's negative 2y with respect to y. So it's negative, and then instead of 0, it's this is getting messy. So let's do it like this instead. Negative 2y with respect to y is negative 2. So this is plus 2. So our curl is 0, 0, 2. All right, so we go ahead and drop that in to the double integral, and we dot product that with the normal vector that we talked about earlier. So this is going to be the double integral of, say, 2 right now. And we're in a cylindrical coordinates. So when you're in cylindrical coordinates, you're going to want to add this piece here. And you're going to want to say, hey, the r is the radius, so it was a unit circle. And then the theta is going all the way around there. So we can pull this 2 out. And we have r, so we can go ahead and integrate that r and plug in 1 and 0. Okay, what do we get for this? We get, well, we get 1/2. So we just get 1/2 there. Now we go ahead and integrate that. Integrate 1/2 with respect to theta, you get 1/2 theta, plugging in 2 pi and 0. You get 1/2 times 2 pi minus 1/2 times 0. This is 2 times pi. This is not agreeing with our other integral here. So me and my carelessness here, where could I possibly have gone wrong? Gosh, let's see. Unit circle. All right, well, it's slightly instructive here because that's kind of the thing you need to be looking out for. And this is the benefit, really, of Stokes' theorem, is that you calculate that line integral like we did earlier, and you get 3 pi. But then you can calculate the double integral of the localized curl at every point on the surface, and you know they're equal. So if you don't get the same answer like I did, you need to just start looking over your work. So let me take a sip of my water here, buckle down and try to identify a little error here. One thing is make sure I got the right F. The F is negative 2y(x)(0). I think we got that part right. Coming down here, let's see, 2 times 1, 2r dr d theta. I don't know, this all looked pretty easy here. 1/2, 1/2 plugging into 2's canceled, pi minus 0. Huh. I wonder what's going on here. It could be that we had this one wrong. Let's see. If we go back here, this was the line integral. So alpha was cosine sine 0. Plug that in, you get negative 2 sine cosine 0 dot negative sine. Ooh, is that right? Yeah, that's right. That's right. Okay. That's right. So we got 2 sine squared plus cosine squared from 0 to pi, 2 pi, I mean. We broke these up. I wonder, did I ever forget about this one? Maybe. Let's see, we reduced this. We added the 1. We multiplied this out. We had 1/2 minus 1/2 cosine 2t. We added the 1 to the 1/2. We got 3/2. That checks out. We did 3/2 t minus 1/4 sine 2t. Good. Then we plugged in 2 pi. Let's be careful here. 2 pi. No, that looks fine. This is good, guys. I'm getting a little slightly worried, but this is good. This is what Stokes' theorem is all about. You know, these two things have to equal themselves. So let's see what we have here. We have, let's see, we have a +2 here. We have the normal vector right there. Trying to see here. Maybe I messed up somewhere here. Aha. I see, guys. Okay, I'm very sorry about that. Took me millennia to find this. But thank goodness for Stokes' theorem, which says that these are equal and that there was a mistake. I'm trying to find the right color here to zoom in here. Okay, so here's where the mistake is. Probably all of you already saw this and you had to sit there and suffer watching me make this mistake. But as I'm telling you, the mistake is very crucial. It's very important to know how to go back. A lot of times instructors and math teachers, they never show you what to do if you get stuck on a problem. Well, I'm blessed because I always make some sort of boneheaded error somewhere. So I'm blessed in that I always get to show my students how to go back and find errors. Anyway, x with respect to x should have been 1 right here. So this should be 1 plus 2. So this should be 3. All right. This should be 3. So 3 times 1 is 3. You pull the 3 out, and this actually looks pretty easy to correct here. This is 3 times pi. That's just 3 pi right there. All right. So anyway, Slightly unplanned event there, but this is how you work Stokes theorem. You calculate the line integral. First, you get your 3 pi. You calculate your double integral of the localized curl. This is the curl. This is the normal vector to the surface that you're working with. And you get that same answer right there.